Compressed Air and Gas Institute presents Efficiency Metrics for Comparing Air Compressors. Similar to the miles per gallon fuel economy rating sticker on the window of a new car in the showroom, the power per flow energy consumption rating of an air compressor is an important piece of information when comparing compressors. Accordingly, the Compressed Air and Gas Institute, also known as CAGI, has developed a standardized data sheet for communicating the efficiency and performance of air compressors. The CAGI compressor data sheet is a uniform and commercially practical means of comparing performance claims during the specification and buying processes. The data sheets have become the go-to, standard resource for comparing compressed air equipment. The power per flow consumption metric of an air compressor has historically been stated as its specific power, which is the ratio of the input electrical energy required to deliver an output flow of 100 CFM at a given discharge air pressure. The lower the specific power of a compressor, the better is its efficiency. Specific power is dependent upon the discharge pressure of the compressor. Therefore, when stating a specific power for a compressor, it is mandatory to note the discharge pressure for which the specific power is given. Let's run an example of specific power calculation for a compressor. A compressor delivers 115 CFM at its rated discharge pressure of 125 psig. This work requires an input electrical energy of 20 kilowatts. Specific power is the ratio of the power in kilowatts required to compress a specific flow in CFM to the rated discharge pressure of the compressor. This ratio is multiplied by 100 to deliver the specific power metric. So, in our example, we divide 20 kilowatts by 115 CFM to get a result of 0.174, which becomes a specific power of 17.4 when we multiply the ratio by 100. This is the specific power information that CAGI datasheets have reported. Here is a sample of a CAGI rotary compressor datasheet that shows the information required for calculating the specific power of the compressor. Rated compressor capacity is found on line 3, and the full load operating pressure used to calculate the specific power is found on line 4. Due to design differences, not all similar horsepower compressors have the same line 4 full load operating pressure. Since specific power is unique to the actual discharge pressure of the compressor, differing full load operating pressures can make it confusing to compare two equally sized air compressors. To further complicate the issue, note that line 5 shows the maximum pressure that the compressor can attain while still delivering its fully rated capacity, but it is not the pressure at which specific power is determined and reported on the CAGI rotary compressor datasheet. This can make a comparison complicated and confusing. In an effort to eliminate the confusion created when trying to compare the specific power, which is an energy consumption metric, between two similar-sized compressors with different rated discharge pressures, CAGI has introduced an efficiency rating value on its compressor data sheets. Isentropic efficiency. The isentropic efficiency incorporates operating pressure and greatly simplifies the process of comparing the efficiencies among several like-sized compressors, each having different full-load operating pressures. As state and federal governments mandate rules for air compressor efficiency standards, isentropic efficiency will be the metric for these standards. Simply stated, isentropic efficiency is a metric that indicates how the actual energy consumption of an air compressor compares to the theoretical energy consumption that an ideal compressor would require to perform the same amount of work. Actual energy consumption is an accurately measured variable. Ideal energy consumption is a calculated variable under ideal compression conditions as follows: no frictional losses, 100% efficient motors, no inertial losses due to speed changes of reciprocating masses on piston compressors, no pressure drops due to flow restrictions, no mass flow losses due to the gas density changes resulting from heat being added to the process. Isentropic efficiency is expressed as a percentage and indicates the efficiency of the compressor at converting electrical energy into compressed air potential energy. Unlike specific power, the compressor with a higher isentropic efficiency is more efficient than a compressor with a lower isentropic efficiency. The better the compressor design is at reducing the real-world losses that are encountered in the compression process, the higher is its isentropic efficiency, and the lower is its specific power. How does CAGI convert specific power to isentropic efficiency? Well, here is the formula for the avid algebra students. The only two variables are the specific power of the compressor and the discharge pressure at which the specific power is determined. In the isentropic efficiency equation, 16.52 is a constant, uppercase p subscript spec is specific power, and lowercase p subscript 2 is the discharge pressure in PSIG. 14.5 is the reference pressure for correcting gauge pressure to absolute pressure. This reference pressure is pressure to the compressor. Lowercase p subscript 2 plus 14.5 atmospheric pressure divided by 14.5 atmospheric pressure represents the compression ratio of the compressor. The exponent of 0.2857 is a constant. This table shows how specific power and isentropic efficiency relate to each other when comparing four 100-horsepower compressors. If, in this example, someone was comparing the efficiency among four similar 100-horsepower compressors, each of which was capable of operating at 125 PSIG discharge pressure, the specific power metric would indicate that compressor C is the most efficient, since its specific power is the lowest of the four compressors. However, if isentropic efficiency is the efficiency metric, then compressor B is the most efficient. The question now becomes, which metric is the most accurate measurement of efficiency? Both are accurate, but the difference is in the operating pressure shown. The specific power is dependent on the operating pressure, and we see compressor C specific power is based on operating at 115 PSIG, while compressor B power is based on operating 10 PSI higher at 125 PSIG. Therefore, compressor C has more favorable specific power since it is operating at a much lower pressure. Keep in mind both compressors have the same maximum operating pressure, but specific power is based on full load operating pressure, so operating pressure is important when using specific power to compare compressors. Isentropic efficiency includes the full load operating pressure to normalize the comparison, and can be utilized for comparing these four compressors without considering the operating pressure. Because compressor B has the highest isentropic efficiency, it will be a better indicator of its efficiency comparison to compressor C, so in a way, it is more accurate from its comparison standpoint. This is because isentropic efficiency incorporates discharge pressure in its calculation. In this example, compressor B is the most efficient compressor at full load. So why does this matter? Over the lifetime of a compressor, the electrical energy that it consumes will account for 75%, 3/4 of its total lifetime cost, including its purchase price and maintenance costs. The efficiency designed into each compressor significantly affects the major cost of compressor operation, energy consumption. Selecting the most efficient compressor for the system demand represents a lifetime of energy savings that needs to be balanced against any purchase price premium for the most efficient design. So similar to buying a car, we also recognize the total cost of ownership includes a substantial fuel expense. So whether you look for high isentropic efficiency or low specific power, finding the optimal compressor is important to your overall operating cost. Note that while we've been addressing efficiency only, there are other factors which may influence your decision to buy an air compressor. Be sure to consult with your local manufacturer's representative or distributor to assess your company's needs, such as size, sound levels, or other considerations important to your company. Visit CAGI.org for a list of member companies that can help with the proper selection of an air compressor. To aid buyers of compressed air equipment, the members of the Compressed Air and Gas Institute implemented a performance verification program. The verification program uses a third-party testing lab to verify manufacturers' data published on the CAGI datasheets is accurate within the tolerances of the ISO 1217 test standard. Check out CAGI.org and view the CAGI compressor datasheets and the list of member companies that manufacture air compressors. CAGI is represented by 45 companies and growing. These are the manufacturers of compressors who publish both specific power and isentropic efficiency. For more information on compressed air, CAGI, as the united voice of the industry, offers educational materials through our e-learning program and the Compressed Air and Gas Handbook, which is downloaded from our website for free.